Section 1 Introduction. In this study, we delve into the world of neural networks and machine learning. We explore how different factors, such as architecture choices, optimization protocols, data augmentation, data sampling, and data ordering, can influence the knowledge a model can extract from a dataset. These factors, when combined, create a unique profile of a model's capabilities. We've conducted extensive experiments to highlight the importance of these factors. We've also built on the work of others in the research community who have provided large and diverse model libraries, such as the TIM or Hugging Face repositories. By comparing numerous pre-trained model pairs, we've discovered that there's often significant complementary knowledge, information that one model, the teacher, has that the other, the student, does not. This complementary knowledge exists regardless of external performance rankings or factors, such as model families, like CNNs, Transformer, MLP, etc., and often concentrates in specific areas of expertise. We found that even models with similar or weaker performance than the student can possess significant knowledge about the data that the student does not have. This discovery naturally leads us to question the potential utility of this complementary knowledge. To answer this, we've conducted an in-depth exploration. Specifically, we've investigated whether it's possible to transfer this complementary knowledge between any teacher and student model, without causing a drop in performance. If successful, this would mean that any freely available or self-generated model collection could be used as an auxiliary resource for improving pre-training. It would also eliminate the need for model-specific transfer methods that require expert knowledge, and remove the reliance on external evaluation measures to avoid selecting teacher models that may weaken the base model, wasting valuable resources. Moreover, it would enable larger models to improve by transferring knowledge from much weaker, lower resource models, without the need for retraining with additional data, large architectures, or sacrifices in speed, fairness, interpretability, or ease of use. We've examined the limits of knowledge distillation for this task, which operates independently of model choices. However, standard knowledge distillation frameworks assume information to be distilled to an untrained student. In contrast, we only wish to transfer knowledge not available in an already trained student model, which may even outperform its teacher. This means that a balance between knowledge gain and retention has to be struck. For knowledge transfer between arbitrary pre-trained models, we've found that common distillation often results in a performance drop for the majority of student models, particularly for weaker or equally performing teachers. This can be attributed to catastrophic forgetting outweighing the benefits of distilling complementary knowledge from the teacher. To strike a favorable balance between forgetting and knowledge gain, we've treated the transfer process as a continual learning problem. We've studied weight interpolation to encourage retention. However, it often imposes too strong a constraint when the teachers have niche areas of expertise or are overall stronger. Therefore, we propose to constrain distillation at the data level by dividing the transfer data into two sets, one where transfer from a teacher is desired, and one where we wish to retain the student behavior. This approach introduces fewer constraints on the model weights to learn from arbitrary teacher context, while reducing forgetting by retaining initial performance on samples where the teacher has limited positive, or even detrimental, impact. Our data partitioning can be achieved without any supervision. With this approach, we've seen significant increases in the success rate for all teacher-student pairings, from 32.5% with normal distillation to 92.5% with data partitioning. Our data level regularization is the only setting which allows for consistently positive transfer from weaker teachers, while retaining the transfer performance of normal distillation for much stronger teachers and even outperforming normal distillation for equally performing ones. In addition, our approach allows for the transfer of specialized knowledge and requires no pairing-specific hyperparameter tuning. Unlike ensembling methods, our approach maintains original inference costs. We've also studied architectural properties and their impact on the transfer process beyond the transfer method, and looked into scalability to knowledge transfer from multiple models. We've found that simple sequential transfer can perform favorably when leveraging our transfer method, achieving clear improvements over transfer from just the single best teacher model. In summary, our contributions are as follows. 1. We've discovered the consistent existence of complementary knowledge between arbitrary models pre-trained on the same dataset, even if model families or performances differ. 2. We've conducted extensive, exploratory studies to investigate the possibility of guaranteed model and performance-independent transfer of the complementary knowledge without performance degradation. 3. We've proposed a successful transfer method motivated through the lens of continual learning, leveraging a confidence-based, hyperparameter-free data partitioning approach. 4. We've provided studies on the relation of general model properties to general knowledge transfer. 5. We've investigated knowledge transfer between multiple models. We will release the code upon acceptance of this paper. Section Summary. In this section, the authors highlight the importance of training neural networks on specific datasets and how it can impact the knowledge extraction capabilities of a model. They compare pre-trained model pairs and discover the existence of complementary knowledge, regardless of performance rankings or model families. They propose a transfer method that allows for the transfer of this complementary knowledge without performance degradation, using a data partitioning approach. Their contributions include the discovery of complementary knowledge, exploratory studies on performance-independent transfer, a successful transfer method, analysis of model properties, and investigation of knowledge transfer between multiple models. Section 2. Related work. In this section, we'll discuss the related work and our approach to studying the transfer of complementary knowledge between different machine learning models. In the early days of knowledge distillation, the focus was on shrinking large models into smaller ones. This was achieved by aligning the soft targets of the larger model. Some researchers suggested using temperature scaling to lower probabilities. More recent work has expanded on this by incorporating structural context. For example, attention transfer encourages similar patterns in feature responses, and some have proposed using regression-guided student feature activations. However, these methods are limited because they require the student and teacher models to have matching architectures. Some researchers have proposed contrastive distillation, which aligns the feature spaces of the teacher and student models, allowing for flexibility in feature dimensions. This approach also highlights the overlap in performance among most distillation objectives. These insights can be applied to distilling knowledge from multiple teacher models, whether they're trained on the same or different datasets. Our approach is different. We're interested in transferring complementary knowledge between any pre-trained models, which is a more challenging task. This is especially true when there are no restrictions on relative performances or architectures, and the initial knowledge should be retained. Some researchers have shown that linear interpolation can be surprisingly effective when the architecture and pre-training are shared. However, this method has its limitations, and selecting the right model through an external validation metric is crucial when dealing with large model collections. We aim to combine model knowledge regardless of model factors and initialization. We do this by using continual learning, which allows us to learn from data streams without forgetting knowledge from previously encountered samples. In recent years, thousands of models pre-trained on standard datasets like ImageNet have been made publicly available. These models vary in all possible training choices, which can potentially impact their generalization. We want to study this impact in this section. We use a tool called TIM, which includes hundreds of models trained on ImageNet under different conditions. We consider the image classification problem with a certain number of labels. We denote the pre-trained teacher and student models as f_t and f_s, with parameters theta_t and theta_s respectively. To evaluate the complementarity of knowledge between any f_t and f_s, we study their performance on the ImageNet validation set. We measure the proportion of samples correctly classified by the teacher but incorrectly by the student. This is what we refer to as complementary knowledge. Using TIM, we randomly selected 466 model pairs covering 301 unique models of varying architectures, sizes, and performances. We found a large proportion of positive prediction flips when the teacher model outperforms the student model. But even when the teacher model underperforms the student model by up to 20%, a high proportion of positive flips can still be found. We also wanted to understand if the complementary knowledge is evenly distributed among classes or if it's grouped within certain subsets. We found that some classes carry a disproportionate amount of context, especially when the teacher model is weaker. For stronger models, the complementary context becomes more evenly distributed. We observe that complementary knowledge between any pair of pre-trained models exists. This knowledge, which a pre-trained teacher can pass to the student, is centered around areas of expertise comprising semantically related classes. This motivates our study of possible general-purpose knowledge transfer tools. Section Summary. Early works in knowledge distillation focused on compressing large teacher models into smaller student models by matching soft targets and proposing temperature scaling. Recent works extended this by incorporating structural context, such as attention transfer and regression-guided student feature activations. However, These approaches were limited to matching student and teacher architectures. In contrast, the proposed contrastive distillation aligns teacher and student feature spaces with flexibility in feature dimensionalities, allowing for knowledge transfer between arbitrary, already trained models. The study found that complementary knowledge exists between any pair of pre-trained models, and this knowledge is centered around areas of expertise comprising semantically related classes. Section 4: General Knowledge Transfer Methodology. In this section, we'll discuss various methods of transferring knowledge, starting with the standard knowledge distillation approach and moving on to our proposed extensions. We'll explain why this problem should be viewed as a continual learning challenge and how it can be extended to multiple pre-trained models. Firstly, let's talk about knowledge transfer through knowledge distillation. This method was first introduced by Hinton and his colleagues, and it involves reducing the difference between a teacher model and a student model's soft targets. This is done by minimizing the Kullback-Leibler (KL) divergence between the two models. The KL divergence is a measure of how one probability distribution diverges from a second, expected probability distribution. We use this method as our base transfer objective because it's still widely used and competitive. Knowledge distillation is often combined with auxiliary classification losses, such as cross-entropy, to stabilize the distillation process. We refer to this combination as ZKL distillation, and the associated transfer as ZKL dist. Transfer, or ZKL. Most research on knowledge distillation considers the transfer from a trained teacher to an untrained student. However, our goal is to transfer knowledge between pre-trained models while retaining the student model's previously acquired knowledge. When we apply standard knowledge distillation to this task, it struggles to transfer knowledge without a drop in performance for most teacher-student pairs. We measure this using the transfer delta, which quantifies the change in the student's top 1 accuracy after the knowledge transfer. Next, we'll discuss knowledge transfer through continual knowledge distillation. This approach aims to strike a balance between overriding the student model and incorporating complementary context from the teacher model. We view this from the perspective of continual learning, which ensures that the student model is flexible enough to learn but stable enough to retain prior knowledge. We use a method called momentum weight interpolation, MCL, to constrain weight updates. This method proves more effective than existing regularizations for continuous adaptation of trained models. In MCL, a slow copy of the student weights is retained in addition to fast weights that are updated during the transfer. The slow weights are updated via weight space interpolation at a predefined frequency and iteration, with a momentum parameter guiding the weight constraint. However, weight interpolation struggles to fully leverage the relative areas of expertise of teachers. Instead, we suggest partitioning the transfer data into samples where the student can benefit from teacher feedback and ones where the prior knowledge should be retained. For samples essential to the transfer of complementary knowledge, we distill from the teacher model. For the other sample set, we distill from the initial, frozen student model, with the goal of retaining the initial model behavior. We assign each sample based on the highest prediction probability for the corresponding ground truth class. In practice, we find that this method provides enough stability to the transfer process where auxiliary classification is no longer required. We also find that this supervised heuristic can be replaced with a fully unsupervised one by assigning samples based on the maximum prediction probability for a sample. This means that knowledge transfer can be performed without access to labels. Finally, we provide a visualization of our data partitioning approach, which we refer to as KL dist plus DP transfer. The overall loss function is then given as a combination of the KL divergence for the teacher and student models, weighted by the data masks. Section Summary. In this section, the authors discuss different methodologies for knowledge transfer. They start with standard knowledge distillation, which involves minimizing the KL divergence between a teacher and a student model's soft targets. They then propose an extension called continual knowledge distillation, which incorporates complementary context from a teacher while ensuring the student retains prior knowledge. This is achieved through weight interpolation and data partitioning techniques. Section 4.3 Multi-teacher knowledge transfer. In this section, we'll discuss the concept of multi-teacher knowledge transfer. With a variety of models available, it's natural to explore how to transfer knowledge between multiple expert models. We propose 3 methods for this. First, we can use all the expert models simultaneously for knowledge transfer, similar to the standard multi-teacher knowledge transfer approach. This method also uses our proposed transfer regularizer to ensure positive transfer. Specifically, we extend the greedy data selection to create data subsets for each expert model. Second, we can transfer knowledge from multiple models sequentially, similar to the continual treatment of the single model transfer process. After each transfer from an expert model, the distilled student model becomes the pre-trained student model for the next transfer step. Lastly, we also explore the use of model soups for architecture-independent knowledge transfer. In this case, the student model is distilled independently from each expert model, resulting in a set of distilled model variants. After the transfer, we perform simple weight interpolation between all variants. In our experimental study, we first conduct a large-scale study of knowledge transfer approaches. We highlight the advantage of a continual learning approach, and particularly the superiority of our data partitioning method. We use a supervised variant for exploration, but we show that the unsupervised variant performs just as well. We also investigate the relationship between model properties and general transfer success, and study transfer from multiple models. We use a high-performance compute cluster with NVIDIA 2080 Tiz using PyTorch 1.13.1 and FFCV 0.0.3 for fast data loading. We perform transfer over a constrained budget of 20 epochs to study methods for general-purpose knowledge transfer with practical requirements. We evaluate different approaches for knowledge transfer and find that standard knowledge distillation is suitable for general-purpose knowledge transfer. However, we find that overriding pre-existing knowledge often overshadows the benefits gained from actual knowledge transfer, particularly when transferring from a weaker expert model. We address this by treating general knowledge transfer as a continual learning task through weight regularization. This raises success rates significantly. However, we find a lack of efficacy when knowledge is specialized to areas of expertise, and when teachers are stronger. We address this with data-level regularization, raising success rates to 92.5%. We extend our experiments to full ImageNet and verify that insights transfer, with data-level regularization performing significantly more reliably than normal distillation. We also provide a more detailed overview, highlighting successful transfer from both stronger and weaker teachers. We also demonstrate that our unsupervised variant of data-level regularization transfer performs comparably and in some cases even better than its supervised counterpart. This shows that general knowledge transfer can be done even without supervision by leveraging data-level continual learning regularization. Our experiments show clear gains when conducting data-level regularization transfer across all kinds of model pairs. We show that gains indeed stem from the transfer of the complementary knowledge between these pairs. Finally, we investigate if and how specific student model properties can facilitate the reception of complementary knowledge. We find that the transfer rate of complementary knowledge has a significant relationship with the model capacity. However, larger models are generally more receptive towards additional context, but models with stronger visual inductive biases are more prone to have their existing knowledge overridden, resulting in a lower distillation delta. Section Summary. In this section, the authors propose 3 approaches for multi-teacher knowledge transfer. The first approach involves using all teachers simultaneously for knowledge transfer, while incorporating a transfer regularizer to ensure positive transfer. The second approach is a sequential transfer process, where the distilled student from each teacher becomes the new pre-trained student for the next transfer step. The third approach explores the use of model soups, where the student model is independently distilled from each teacher model and then a simple weight interpolation is performed after transfer. The authors conduct experiments to evaluate the effectiveness of these approaches and find that data-level regularization and continual learning techniques improve knowledge transfer success rates. They also observe that the transfer of complementary knowledge between teacher-student pairs drives the transfer gains, and that the model capacity has a significant impact on the reception of complementary knowledge. Section 5.2 Knowledge Transfer from Multiple Pre-trained Models. In Section 5.2, we delve into the concept of knowledge transfer from multiple pre-existing models. We conducted our study on the full ImageNet, using sequential and parallel KL plus DP transfer methods, and a model soup variant that interpolates between transferred student variants. Our experiments involved 3 student and teacher models, with a particular emphasis on transformers. These models have demonstrated a high capacity for knowledge absorption in our tests. The results, as shown in Table X, are compared with the performance of a single teacher transfer. We discovered that students can consistently learn from each teacher when the transfer is sequential. However, as the student's performance improves, the benefits start to decrease until they reach a plateau. This is because the student starts to forget more as it moves further away from its initial pre-training. Despite this, the sequential transfer from 3 teachers results in an average improvement of 59% compared to the best single-teacher transfer. For example, the transfer delta for the twins model increased from 0.26 to 0.65, and for the PIT-B model, it increased from 0.86 to 1.04. On the other hand, we found that the basic KL-DIST transfer method was not successful in a multi-teacher setting, highlighting the advantages of the KL plus DP transfer method. We also found that the order of the teachers didn't significantly affect the knowledge gain. However, our experiments suggest that starting with the strongest teacher can lead to more forgetting, as the model moves away from its base knowledge more quickly. In contrast to sequential transfer, parallel transfer from multiple teachers did not improve performance compared to the best single-teacher transfer. This is because the subset regularization did not retain enough samples for active knowledge retention. Lastly, we found that the method of averaging the weights of student variance, each distilled with a respective teacher, performed the worst. We believe this is due to a lack of ability to interpolate and a subsequent decrease in knowledge retention.